said, we're recording this. It's going to wind up connected through our website. You'll all get a link. We encourage you to use it. I mean, if you find the tool useful, reach out, grab the link. It's probably going to be up on YouTube. Review it with your colleagues if you have a spray dryer responsibility. We want to make sure that we're all out there in the world working as safely as we can. So there we are. Let's see that I can advance the screen. Can I advance the screen? I can advance the screen. So here we go. We want to have timely topics when we do these webinars. So we figured dryer safety is always a good one. And as we prepared this over the last few weeks, we got some examples. So really this is happening all the time. We want everyone, we don't want to point out the mistakes of others. What we want to do is learn from them. So, want to use these as real live examples for all of us to stay vigilant with our plants when we're out there working with them. So this is as recent as July 29th. So just over 2 weeks ago, Sibley, Iowa. It was Iowa Drying and Processing, and they had a spray dryer fire in their egg processing plant. So, this isn't the rare thing that only happens once in a while. This is happening, unfortunately, regularly. It's so new, I haven't found out what was the cause or any of that, but it does remind me certainly to stay vigilant when I'm designing plants, when I'm working with clients on their existing plants, and when I'm talking with folks like you in a course like this, so that we can all keep our plants running. Unfortunately, there was a week before that. So Tate and Lyle had a dryer fire in Decatur, Illinois, July 21st. Crews were called, fire department's there, and the quote in the small print from the left of the screen is that they believe it was a dust explosion in a dryer. So that's what we're dealing with here. We're dealing with explosive dust. So again, live examples. A few older pictures that are a little bit close up after the events have happened. So this is a spray dryer after an explosion in a dairy plant. This is the scene you don't want to see when you're driving up. This is a spray dryer fire in a dairy operation, all with known sources. They've been studied, all with, thank goodness nobody injured in any of these that I'm aware of, but also understood reasons that these fires and explosions happened, and lessons to learn about preventing them in the future. Spray dryers have all the conditions needed for a process fire, possibly an explosion. We definitely have the oxygen and fuel, oxygen in the air. The fuel is our powder. In talking about a dust explosion, it's a confined space, so a drying chamber, a bag filter. The powder's not just sitting, on the bottom. It's in a dispersed cloud, so we have dispersion, and all we're looking for is a cause of ignition, and that's what's in our control to try to prevent, from happening. Again, I've used the word vigilant a couple of times. I believe in it. When I'm visiting a factory, keeping my eye out for things. If you're responsible for a factory or a spray drying operation, being vigilant and keeping your eyes open and correcting things yourself on a day-to-day basis, and working with your colleagues to do the same. I would say it's an observation of mine that I've seen, more fires and explosions or events happen during the holidays. So when maybe your first shift operators are, getting the first dibs on Christmas Day off or Christmas week off, and your second or third shift operators are either alone for the first time in the, running the plant or the like. I'm seeing more of these events during the holidays. And what I also am noticing is, because I'm not in a plant. If you're an engineer, you might not be in a plant as often. You might be working from home. There's a lot of experienced eyes that aren't walking through the plants regularly here during this time of COVID, like it's a holiday. And I think we've been seeing this ramp up in events at the plants. So recognize that this period of time that we're in right now is like the holidays, where you're asking your regular frontline employees to take more responsibility. It's the time to keep training up. it's the time to keep awareness up. So that's my my little pitch on being vigilant right now. As we go through this 30-minute presentation today, keep in mind when you're working with a spray dryer, historically through fires I've investigated, events I've read about, and data that's been collected on fires and explosions, the spray nozzles in a nozzle atomization dryer have been the source of 90% of fires and explosions. They may be leaking, there may be improper assembly, but the spray nozzles remain the primary problem. Plugged vessels, so bridged cones of drying chambers, cyclones, bag houses, might be the second most likely at 5% of all causes of fires and explosions. And then you could lump everything else into that last 5%, all other causes. That's a rough overview of that, but it means as we talk about these things, we're often talking about being vigilant about spray nozzles, spray nozzle procedures, and maintenance and the rest. A little bit about the rules that guide us and govern us. This is NFPA, the National Fire Protection Association. They write the standards that we as dryer designers follow. So we might follow NFPA 68, which is the standard for explosion protection and venting. So if you have a dryer with vent panels on it, the design of those vent panels was guided by NFPA 68. And the dryer designer of your dryer probably consulted that, used the formulas in there, and designed the dryer that way. It's been in place for 20, 30 years. But if you have a dryer that's older than that, it may not. These standards may not have existed before then. NFPA 69 is another standard that guides dryer engineers and dryer designers. And that's if you choose to use an explosion prevention system. So that might go by the brand name Fike or Fenwal or something like that. You might have these canisters all over your dryer. And this NFPA 69 guideline and standard would be what would have guided that design. Now, this standard is built upon others. It's built upon NFPA 652, and 652 is a lot newer. The latest issue is 2019, but it's only existed for probably the last 3 or 4 years. It says when you have a plant that has combustible dust, like a food powder or something like that, an agricultural product, then you must use 68 and 69 where appropriate. But it also speaks a lot about the fundamentals of dust. These would be good guidelines to have available if you're an engineer or a manager responsible for an operation. There's a lot of good tidbits in there about what not only what your responsibilities are, but how you might carry out those responsibilities. And that's built upon another newer standard. So that's NFPA 61, the 2020 version. So that's the standard for the prevention of fires and dust explosions in agricultural and food processing facilities. So that's the new one that's out there. Also great guidance of how to do things. Another reference or resource. I want to leave you with your own tools for understanding not only the hazards in your plant, but how to mitigate the hazards. So here's 3 tools by the National Fire Protection Association. Because some of these are new, they're always being interpreted new. There's people speaking about them. So one of the great resources that writes about these, sort of digests these complex things and writes articles about them, I usually go to Powder and Bulk Solids, either the magazine or the website, to read their discussion of these, their interpretation of them, their warnings. They're really quite good articles. So NFPA 652 was the middle one from the last slide, the fundamentals of combustible dust. They have a good article on the website. This one's a couple of years old because it says the clock is ticking, because you get a period of time to implement these standards at your plants, new procedures, new operating procedures, new safety procedures, things like that. But at a certain point, one has to have them in place. So on NFPA 652, the clock is ticking. Their article I reread yesterday on NFPA 61, the new 2020 edition, there's a good discussion of what are the new things that have come in with that. And I would, instead of me interpreting it and taking up time, I'll point you directly at it so you can look it up yourself. But I just Googled NFPA 61 and quickly came to the Powder and Bulk Solids Magazine website and found the article. So a little bit of extra reading or homework there for you, and certainly an excellent resource. If I were to say, one thing about these safety systems, do you have them? Do you not have them? Once you have them, it's the maintenance of them. The difference between maintaining your safety system, having an event, and being able to, so having a fire or explosion, and being able to clean it up in 12 hours, 24 hours, 72 hours, but being able to clean it up and get safely back working again and processing, or having an event, having your safety systems not maintained properly, and having a month or 2 or 3 of being unable to operate. So I really can't underemphasize, I really must overemphasize, the maintenance of these safety systems because of the impact they have. It would be a shame that you have them and they would not be able to do their job. An example here, this is a drying plant. I went to see this one after, these are my pictures on my industrial tourism visit to this plant after the fire. What we found were they had overpressure doors and they had been bolted shut. Not only had they been bolted shut, they'd been caulked shut to prevent CIP leakage. Nobody thought to do the maintenance on the doors so that they wouldn't leak. When the gaskets were installed correctly, they said, we've got to get running, we're just going to bolt them shut. Not only did they have that, but the water deluge system, so the water safety system, had not been tested in recent memory. There was not a person I could ask who remembered it ever having been tested. So it probably went back 10 years that hadn't been tested. So what was the outcome? They had an event, fire turned into an explosion, and they lost 4 months of production. It was not only the drying chamber, which I'm showing you here, it was cyclones, fluid bed ductwork, fans were burnt up, wiring and conduit on the outside were burnt up. It was a massive undertaking to rebuild it, and 4 months was lucky. So had they done the maintenance, had they kept their systems in good working order, they would have been running again in a few days. Another example, safety systems, so explosion venting worked, water deluge didn't work. And it was a minor thing that was found that didn't work in this case. This is a bag house that was replaced, had to be replaced. But regular testing of the water deluge probably would have discovered the deficiency in the system and prevented the necessity to replace this. So again, no naming names, but an example for us all to learn from, that it is expensive for the equipment, it's expensive for the operation because you're losing processing time, and it's not really necessary that this happens. So what am I saying to you on maintenance? If you have overpressure doors, so doors you can open and close again and reuse, or you have vent panels, so single use rupture panels. If you have doors, they probably have shear pins on them. Please don't replace them with bolts or anything like that. Understand that they are shear pins. They're designed to open at a certain pressure. And if anything stronger than that is put in there, you're in jeopardy of rupturing the vessel that this is meant to protect. So shear pins, please know your spare part numbers, know where they are in the spare parts system, and use the shear pins that were intended. If it's vent panels, those are meant to be replaced with some regularity as well, but do check those. There should be an inspection regime on them. Gaskets, whether it's doors or panels, Gaskets must be maintained. They should be replaced when necessary. On the doors, don't use caulk. If you're getting some CIP leakage, you know, caulk is glue. Don't glue your safety doors shut. Sometimes the overpressure doors have sprung hinges. That's another item to be maintained if you have overpressure vent doors. Beyond that, the doors or the panels are going to be ducted to the edge of the building. Don't obstruct that duct. Don't store things in there. And if you, where you do have that duct, make sure the access door is properly secured. We want to vent this explosion out of the building. If your vent duct access door is open, because you're looking for CIP leakage, because the gaskets haven't been maintained, now you're not directing an explosion out of the building, you're directing it into the building. So do be mindful of that. Water safety system or an over temperature protection system. This is to put water, spray water into your vessel when you get high temperature. They'll be on drying chambers, they'll be on bag houses, they'll be on fluid beds, and they should be tested regularly. So you've probably got a nearby control panel with a few switches on it. It's maybe checking air pressure and water pressure to make sure things are going to operate safely. And then it's going to keep an eye on the temperature. Please test them regularly. Test the panel, see that the pneumatics remain connected, see that the water valves can open and close. It's great that you test the electronics, but I've seen it before where now you need the water valve to open and it hasn't moved in 5 years because nobody has stroked the water valve. So do check the entire system. Create a high temperature condition. You can do that with a hot block from the laboratory. Immerse the RTD into a hot liquid or a hot block and really set the system off. Test the chamber, test the fluid bed. I'd say there's no reason one couldn't think about testing them every time you CIP. Once you're hooked up for CIP, I'd say try to get to it every 3 months. With a bag filter, try to do it with every filter change. And again, check all parts of it. Test the air pressure switch, drop the air pressure down and see that you get an alarm. Test the water pressure and visually check it. I've been involved where you found out that a system didn't activate and you quickly find, or didn't put water into the system when it activated, and you find that hand valves are closed. So do that check every once in a while. And then in general, maintain the documentation. These systems often have a battery backup, so maintain the battery backup. And then, you know, for relays or switches, pressure switches, whatever may be part of the system, make sure you have the spare parts for them on stock. So that's my words about maintenance when it comes to these safety systems that you may already have on your dryer. Let's make sure they're able to run and you don't wind up in situations like those early examples. A little bit tangential, but there's a spray dryer on fire for you. What happened here? Lockout tagout procedures weren't followed. Somebody was welding on a stainless steel door frame, and it set the insulated building panels on fire. That raged up through the inside of the building, and that wall tipped down, fell down onto the truck receiving bay, and then the fire raged through the rest of the plant. So lots of ways. This is not really spray dryer safety. This is sort of plant safety. But while we're talking about it, I ran across this example while I was preparing things. So I thought I'd show this one as well. So a little bit about explosions themselves, a little bit about the science of it instead of just examples. So what's a dust explosion? A dust explosion is where one particle in a cloud, like cloud of dust inside your drying chamber, one particle ignites. Let's not talk about yet why it ignites, but let's assume one particle ignites like we're showing here on the left. If you have the right conditions, so a dispersed cloud of the right density, then the next group of particles will catch on fire, and finally it'll spread and more will catch on fire until it rages through your dryer and it creates a pressure wave. Now, The pressure wave is really the air in between the particles heating up. So this explosion that, whether you've seen it in a video or heard a presentation like this, maybe seen a video in a presentation like this, that what we feel is an explosion, that pressure wave that comes out of this, is really the air heating up between these particles as the next particle burns and then the next particle burns. But that's sort of the picture you have to have of a dust explosion. One particle starting and then a wave of particles going out from that. Now, you have some limits to that. So one thing to know about, so a little science for those that are attending that are a little science hungry. So you have a lower explosivity limit. That's the leanest fuel mixture. That means the lowest fuel mixture where you can have one of these dust explosions or deflagrations. Anything below the lower explosivity limit and the mixture is too lean, the particles are spread too far apart. The air acts as the first particle catches on fire, and the air acts as an insulator, and the next group of particles can't catch on fire. Then you're below the lower explosivity limit. And what that means, it's particles powder specific. So if I talk about milk powder, sorry that I've jumped into metric, but that's about 60 grams per cubic meter for milk powders. Anything less than that, and you just can't explode. And it's different for different powders. So sugar is very explosive. You can have 1/4 the amount of powdered sugar in the air and sustain an explosion. Just to give you some feel for what it means, 60 grams in a cubic meter is about the same as 12 teaspoons in a cubic meter. So like a cup of powder in a cubic yard, or a half a cup of powder in a cubic yard, is enough to sustain an explosion. Anything lower than that, and you can't have one. Now you have the reverse as well, the upper explosivity limit, the richest, highest fuel mixture that can cause a dust explosion. Anything above that, and the powder's too dense. So here we're talking about 2,000 to 6,000 grams, or 2 kilograms, 4 pounds, to 12 pounds of powder in every cubic yard. It's like when you talk about, could you set the phone book on fire with a match? Sure, paper burns, but the paper's too dense to light with a match. So if you're above the upper explosivity limit, you have too much fuel and you can't really set it on fire. So in between the two, in between the lower explosivity limit and the upper explosivity limit, you have a zone of powder loading in the air that you could call the Goldilocks zone. It's sort of the opposite of that because it's the danger zone. But you in between those two levels, you can have that explosion. So a little bit of science. One number, if you have a piece of paper in front of you right now, write down the number 60. So that's the lower explosivity limit for milk powder, because I'll be asking you about that a couple of slides down in the future. So environmental and nuisance dust. So now we have our spray drying plant, and we've gotten some dust into the room. We've opened a manway, maybe a gasket's leaking. Who knows what upset condition you may have had. What does it mean to have dust in the room? Because that's a natural hazard that we might face in a spray drying plant. And what does it mean to housekeeping? So here's that question again. Of the 60, this is where I'm asking you to remember the 60. So how much environmental dust do you find acceptable when you walk into a dryer room? So you're attending this webinar probably because you're responsible or have some responsibilities for a spray dryer. If you walked into the room and you saw dust on the ground, at what level, what depth? Does it have to be 1 inch deep before you get worried about it? Does it be 2 inches deep? Well, the answer is right there. The answer is 1/16 of an inch of dust. If you have 1/16 of an inch of dust in the room, 1.5 millimeters, that's generally determined to be a problem. Why? Because that's enough dust to raise up into a room to get you into the Goldilocks zone or the danger zone between those explosivity limits. So if you have your powder and you check the density, so this is metric, grams per cubic centimeter, you can know the density of your powder in pounds per cubic feet, and you want to know how much powder that is to cover a square meter. So that in this case, when we're at 1/16 of an inch or 1.5 millimeters, That gives us between 675 grams and 930 grams. So between 1.5 pounds and 2 pounds of dust per square meter when it's a 1/16 of an inch thick. And now you have an explosion in the plant. And that dust is raised into a cloud in the room. So now you have a cloud in the room raised by a concussive explosion, your 1/16 of an inch that was moments ago lying on the ground. In a room with a 10-foot ceiling, that's going to give you 225 to 310 grams per cubic meter of dust in the air, of dust in the dust cloud. And that's definitely above 60 and below 2,000, those two numbers we saw a couple of slides ago. So when you have a 1/16 of an inch of dust in a room with a 10-foot ceiling and you raise that dust, you have a dust cloud that's strong enough to sustain an explosion. More than that, if you're in a room with a 30-foot ceiling, you're still above 60, not much above 60, but you're still above 60 when you've had a 1/16 of an inch of dust raised up into a cloud that fills the room. So the 1/16 of an inch of dust seems like nothing. You might walk past it without thinking, I need to vacuum up off the top of the equipment, or I need to vacuum or sweep or wash the floors. But a 1/16 of an inch of dust is enough to fill a room where if you had an ignition source, you could have an explosion in the room. And I bring this up because we have those days where the dust gets out of the spray dryer. We've had to open a rotary valve. We've had to open a manway, and we get dust in the room. We've got to clean those up. We still may have to access the equipment, but as soon as we're done, we must follow the good housekeeping procedures of cleaning up. So other things, here just examples for you. I wanted to make this a very practical sort of presentation, keeping the science and numbers to a minimum. So ignition sources, open flames, this has happened. There used to be a practice where you used metal scoops to reach into a fluid bed or reach into a bin and get a powder sample. And they used to be sanitized with methylated spirits. And then you light the scoop on fire and you burn off the spirits, and that sanitizes the scoop, just like your dad might have sanitized a pocket knife before digging out a splinter or something like that. But that used to be the procedure. And it has happened where you can't see the flame of a methylated spirit. That's like auto racing fuel. You can't see the flame from that. It has no color. And that invisible flame was still alight when somebody put a scoop into a fluid bed and ignited an explosion. So that procedure is long gone, but one has to think of these things. One has to remember them so we don't repeat them. People worry about sparks, static electricity, but also other kinds of sparks. You do need a certain amount of energy to ignite a powder. For dairy powders, it tends to be about 50 millijoules that will ignite a dairy powder. Each powder has its own level. Static electricity generally doesn't have enough energy to reach that threshold and ignite dairy powder. So although very good practice to have everything in your plant grounded, grounding straps across flexible connectors and the rest, the generally accepted science, and there's still some open debate on it, so please do not take this as the final word, but generally accepted that that a static electricity spark is not enough to ignite a dairy powder. Now, if your powder has a different energy of ignition, well, that's a whole different story. Remembering that insect zappers that we have around plants, now we talked about dust in the room a moment ago. If that dust gets near an insect zapper, well, there you have ignition with dust in the room. Impact from tools, sparks from electrical systems, all the like, all things to keep in mind when we're working around our flammable dust, combustible dust in our spray drying plant. Prevention, an ounce of prevention, worth a pound of cure. Thank you, Benjamin Franklin. One of the more modern things, so I'll leave you with something forward looking, one of the more modern things that's out and available these days so that we can think about preventing a fire, because so far we've talked about we're going to have an explosion or we're going to have a fire. So let's use water or rupture panels to protect us. So that's the protection side of things. This is a few thoughts towards prevention. So how do we stop these things before they really get started? So carbon monoxide detection, so not carbon dioxide. Please don't get those confused. They're very similar. Carbon dioxide has a function in safety systems as well, like fire extinguishing. But carbon monoxide is produced by combustion. So if you had the beginnings of a fire in your dryer, but it's not big enough yet to really be, you couldn't smell it yet. You certainly couldn't visually look in there and see a flame or anything, but there's a little bit of a smolder. A smolder would produce carbon monoxide, and that can be measured. So if your operation is in the mindset of prevention, then CO detection is definitely a possibility. This is, I would say, more on the cutting edge of systems or solutions that one puts on spray dryers. Even most brand new spray dryers aren't considering this yet, but we want to have it in front of the idea in front of people and know that there are things out there. So carbon monoxide detection is definitely a cutting edge way to think about prevention instead of just protection. And then sort of the last slide I have for you today, nozzle testing. I started this by saying 90% of spray dryer fires and explosions start at the nozzles. Nozzles that have been incorrectly assembled, nozzles that are using worn parts. What we find, so we're saying 90% of it starts with the nozzles, and 90% of those could be detected because they're an assembly problem or whatever. The instant you start spraying, you know you have a problem. So it's not that nozzles crack an hour or 10 hours into production. It's that the problem could be known at the moment you start spraying. So a lot of people have dealt with that by putting cameras in. Cameras are great, a great safety feature and function. They're somewhat self-explanatory, so I've not dealt with them here today. Could be a topic for another webinar perhaps, but if you use cameras to keep an eye on the sprays, and most problems happen right when you start spraying, why not test the spray before you put it in the spray dryer? Why not test your nozzle under pressure before you install it? So that's the picture of the test rig. So this is at a 3 nozzle spray dryer, and this tank is used for CIP, and at the end of CIP, the operators assemble the nozzle lances for production. They put the spray bodies on there and the orifices and the swirl chambers in there, and then we connect it to a test pump that takes it up to, let's say, 500 to 1,000 PSI, and we can look in this window and see each of the nozzles spraying. If we see a good spray pattern, we know it's safe to install that nozzle in the dryer. If we see a bad spray pattern, we know we might need to disassemble it, check the parts, and test it again. So a simple prevention method, knowing that 90% of your problems start with the spray nozzles, and 90% of those problems could be noticed if you tested your nozzles ahead of time. So a simple test procedure under pressure. You could have multiple, you might be worried, oh, that's going to take us a little bit of time. We don't have that time. We got to get back into production. Well, if you had multiple sets of nozzle lances, so if this 3 nozzle dryer had 6 nozzles, and yesterday's washed 6 were put into the dryer clean today, as soon as the feed line is clean, you could connect them up and run, and then test these 3 nozzles that are in the tank right now at some point this afternoon and get them ready for tomorrow. So we don't see the pressure to get back into production is a reason not to do this. We can find some workarounds for that. So we've seen this implemented effectively. You can't tell how many dryer fires you saved, but the people that are implementing this type of nozzle testing procedure are doing it rigorously and are thriving. So no fires, no explosions. So with that, I'm going to say thank you very much for listening today. If you have any reason to reach out, you can reach Missy or I or any of our engineers at info@caloris.com. You can reach me personally at jkent@caloris.com. And Missy, I'll turn it back to you, and we can take some questions if there are any.
Okay, I don't see any questions yet. And again, if you want to ask a question, we have the Q&A feature enabled here. But one question did occur to me while I was listening to this presentation. With what frequency would you encourage a dryer engineer to put eyes on the various components you've been talking about today that require inspection on a regular basis? How regular of a basis? Is it daily? Is it weekly?
Good question, Missy. Thank you. I would say like those maintenance slides that I showed earlier. I think there are certain things that the operators could look at daily or weekly. Leaking at gaskets, things like that. I think then you start talking about the responsibilities of the maintenance staff. That becomes maybe weekly or monthly things, just sort of the walking of water lines to make sure the hand valves remain all open, things like that. And then whether you're the plant engineer responsible for, let's say, the water deluge system, and you're going to test it because you have a CIP coming up, you're going to test it at the beginning of CIP. If you have a dryer that CIPs frequently, let's say once a week, you can stretch that testing out and do it once a month or once a quarter. But if you're that sort of normal dryer that washes once a month or once a quarter, then I would say, having the plant engineer or the dryer responsible engineer testing with every dryer CIP, the water deluge system, I think that would be a reasonable, or it's a reasonable expectation, but sort of a forward-thinking, proactive one. If you haven't done it in a year, I would start to say that's then it's something you need to attend to.
Okay, and you mentioned some parts of the dryer that usually could present a problem. Are there any parts that you recommend replacing proactively, or at least having on? You mentioned a couple having on hand as spares for as needed, but any in particular that come to mind as being handy to have on hand?
Yeah, I think every plant that has overpressure panels, so single-use explosion vent panels, should have those panels on hand. Enough for at least one of the vessels, because it's going to be 4 weeks or 6 weeks to get replacements, possibly from the manufacturer. Would be good perhaps for all to be able to replace all the panels on one spray dryer. So drying chamber and bag filters, for instance, on one spray dryer. I would also say, in light of your question, that single-use rupture panels do get weaker over time. They're heated and cooled every day. They go through a little bit of pressure cycling. They are a very thick foil, and therefore over a year or 2 or 3, they get weaker, and a corner may break loose and leak. Now, that's not a safety problem, but it probably is a hygiene problem. You might have CIP fluid leaking out of there. You might have powder leaking out. And you want to handle that on a day you're prepared to handle it. You want to handle it proactively. So to think about replacing your overpressure vent panels my experience is sort of to say they might start getting weak in about 2 years. So to put them on a 2-year cycle for replacement will have you in a very proactive place in replacing those. So some thoughts to that. There you go.
All right. I just had a question pop up. Any ideas for testing baghouse deluge system without a bag changeout if the changeouts are infrequent?
Yeah, fair question. Thanks, Kevin. Bag houses, most bag houses are getting a change once a year, 9 months to 12 months, something like that. And that's going to have to be frequent enough, right? That's going to, for the real big test of wetting things down. Now, if you can make your bag house last longer than 12 to 16 months without bag changes, you probably have something good going on, and I want to learn more about what you're doing. But if you're more like the average, where it's every 6 months, 9 months, 12 months to change the bags, then you're probably testing your water deluge frequently enough to consider yourself proactive and safe. Um, if you want to do more testing than that, I would say you could do a dry test, right? You disconnect the water, you blank off the water line, um, do the activation test, so you see all the logic work, the electronics work, you see the nozzles stroke, open and closed, but you just do it without water. So that would be my recommendation on testing a deluge system or a water safety system on a bag house when you're not changing the filter bags frequently.
Okay. Um, We still have a few minutes, so if anybody has any additional questions, feel free to type them into that Q&A feature. In the meantime, as Jim mentioned, I have been recording this session. We'll make it available on our webinars page, which is caloris.com/caloris-webinars. It should be up within 24 hours. And this is the last in our current series of webinars. So we want to thank everybody who has joined us today and those of you who have been regulars at our webinars so far this summer. But stay tuned because we do plan to offer more webinars in the future. If you're not already receiving our weekly e-newsletter, I encourage you to join our mailing list, and you can do that by scrolling to the bottom of any page on our website and entering your email address where prompted. Again, it's just one email a week. It's topical headlines from the industry, resources for plant managers, and announcements such as upcoming webinars. If you had a question that you did not feel comfortable asking in this webinar setting, again, you can reach us by sending email to info@caloris.com. That goes directly to me, and I'll forward on your question to Jim or whomever is the best to answer it. And we also are actively soliciting topics for webinars. So if a topic based on this presentation comes to mind, or any other technology questions you might have that could be a potential webinar topic, please do let us know. We've enjoyed offering this series, and we want to bring you topics that are of interest to you. So with that, I don't see any additional questions. I'm going to go ahead and end the session. Thank you, Jim, and thank you, everybody, again.